Hello, I'm Kelly, and I'm going to talk about our work on a Bayesian approach to learning bandit structure in Markov decision processes. There is increasing interest to apply reinforcement learning algorithms to real-world problems, including mobile health and online education. RL algorithms are often developed assuming the environment falls strictly within a contextual bandit or an Markov decision process framework. In MDP settings, the choice of action can affect the probability of visiting future states, while in contextual bandit environments, the choice of action doesn't affect which future states are visited. In many interesting real-world problems, though, it's often unknown which one of these frameworks one should assume. For example, consider a mobile health application aimed to help users increase their step count. A few times a day, the RL algorithm uses the user's state information to decide whether or not to send the user a message encouraging them to take a walk. It's not immediately clear whether to use a contextual bandit or an MDP algorithm in this problem, as it's not clear to what degree previous notification decisions will affect what future states the user will visit. Assuming the wrong framework can lead to inefficient learning, or worse, the algorithm could never learn the optimal policy, even with infinite data. Here we illustrate the cost of assuming the wrong framework. We compare a contextual bandit posterior sampling algorithm and an MDP-based posterior sampling algorithm. We plot the cumulative regret of these algorithms in both a contextual bandit and an MDP environment. The contextual bandit environment is identical to that of the MDP environment, except the transition probabilities are uniform over all states. As you can see, in the contextual bandit setting, the MDP algorithm has much greater regret than the contextual bandit algorithm. And in the MDP environment, the contextual bandit algorithm never learns the optimal policy. In this work, we consider the problem in which someone deploying an RL algorithm in real life is unsure whether the environment is that of a contextual bandit or an MDP. Our algorithm is based on posterior sampling and utilizes Bayesian hypothesis testing to learn whether the environment is that of a contextual bandit or a classical MDP. The null hypothesis is that the environment is that of a contextual bandit, and the alternative hypothesis is that the environment is that of an MDP. We allow practitioners to choose a prior probability between 0 and 1 of the null hypothesis being true. Additionally, practitioners choose two RL algorithms, one contextual bandit algorithm and one MDP algorithm. Our algorithm uses a posterior sampling approach. At the start of each episode, an environment indicator is sampled from the posterior probability of the null hypothesis. If the environment indicator sampled returns that the null hypothesis is true, meaning the environment is that of a contextual bandit, then for that episode, we choose actions according to the contextual bandit policy. Otherwise, we use the MDP algorithm to choose actions for that episode. Our algorithm essentially alternates between a contextual bandit algorithm and a full MDP algorithm. Additionally, when posterior sampling algorithms are chosen for the contextual bandit and MDP algorithms, then our Bayesian hypothesis testing RL algorithm can be interpreted as a posterior sampling algorithm with an additional prior that can upweight the prior probability that the environment is that of a bandit. Thus, the Bayesian regret guarantees for standard posterior sampling for MDPs can apply in this setting. Here we show simulation results comparing our algorithm to others in both a contextual bandit and an MDP environment. Blue is the contextual bandit posterior sampling algorithm, which is the best performing algorithm in the contextual bandit setting. Green is the MDP posterior sampling algorithm, and red is our Bayesian hypothesis testing RL algorithm, which we can see outperforms the MDP algorithm in the bandit setting. In the MDP setting, the contextual bandit algorithm cannot learn the optimal policy, and our Bayesian hypothesis testing RL algorithm performs similarly to the MDP-based algorithm. Our simulation results show that our Bayesian hypothesis testing algorithm can perform well in both the contextual Bandit and MDP environments. Thanks for listening to our talk and see our paper for more details.